Denis Ovchinnikov from the Stevens Institute of Technology speaks of interpretation by PE formulas and the Diophantine problem over algebraic structure.
It's my great pleasure to speak here in a great city. I've never been to St. Petersburg before, so I'm very excited about it. And the conference is great too, so thanks to the organizers for inviting me. And yeah, I will talk about the Diophantine problem over algebraic structures, and the motivation is solving systems of equations, of course, over some structure. And just to give some examples, Gaussian elimination provides you an algorithm to solve equations over abelian groups. Quantifier elimination allows you to solve equation, or more generally first-order formulas over a bunch of structures, for example, algebraically closed field and so on. And from more non-trivial results, Makarian-Rasborov algorithm solves equations over free group of finite trunk. So I'm not going to speak about it too much, but yeah, it's a great algorithm. Later it was shown that the first order theory is also decidable, but it took almost 20 years, I think. And now to the main topic of my talk is undecidable part of solving systems of equations, and the first result of course stems to the problem, the fact that there is no algorithm to solve equations over Z as a ring. And there are a lot of examples other than Z known now. But most of them are really commutative associative rings with identity. So, for example, a lot of interest is the problem, the Diophantine problem over rings of algebraic integers. Of course, rationals is a very famous open problem. And there are some known results about polynomial rings and stuff like this. But really, I want to focus on other structures. And the main examples would be groups and non-commutative rings. And in this field, there are really not a lot of examples with non-undecidable Diophantine problem. And they are very sparse, and there is no really method to approach them. So, and also it depends on the exact definition of the Diophantine problem, which I will denote by Diophantine. Because in this classical setting, you really can do quite a lot with equations. For example, you can write something like f is not equal to 0 as an equation in, for example, Z. Or something like f is greater than 0 is also an equation. Also, a system of two equations, or finitely many, you can also write it as a single equation because f squared plus g squared in Z. But in other structures, it's really different. So I will avoid this, and of course this. So I will just talk about equations, and I will talk about finite systems of equations, because it's really different. Next example will show, not show, but one of the examples is a group of upper triangular matrices over Z, unique upper triangular matrices over Z. And there was a work of Mundunchin, Hao Liang, Michael Shapiro, in very recent work, surprisingly, that shows that systems of equations over this group are indecidable. And moreover, addressing my last remark, they show that single equation over this group is actually decidable. So really, it's a lot different in groups or non-commutative rings. So I won't bother with it much. I will just talk about finite systems of equations because it's much easier to work with them. And the main idea, if you multiply these two matrices, if you look at this last term, you can see that there is addition here, and there is also multiplication. So really, what they do is kind of interpret. They don't specifically say so. But really, if you write commutator of these two elements. This would be an element like this. And in the end, it would be A1, B2 minus A2, B1, 0, 0, 0, 0, 0. So what you can do, you can write precisely an interpretation of ring of integers in this group. And how you do it, you try to define this last corner just by saying there exists xy such that commutator of xy is equal to your element g. This obviously defines this subgroup. And addition on this subgroup is already, or multiplication of this subgroup defines your addition of integers. If you look at these last variables, if all a_i's and b_i's are zeros, then you just get addition here. And multiplication you can quite easily define using this. So what really is surprising is that they don't express it in this way, and they spend like 10 pages writing down this interpretation precisely and rewriting all possible systems of equation over Z, or over Z equations over this group. So really, this was a motivation for us, and we tried to generalize these interpretations to other groups and rings. And interpretations, so usual interpretations, you all should be, I think you all are familiar with them. If you have a structure and you have a subset of n to the n, then if there is a formula, it's true if and only if the tuple is in your set, then it is definable. And if you have a structure, then if the domain is definable, graphs of all of the functions, predicates, and that's all are definable, then we say that the structure is definable. So really this is a definition of a structure. And moreover, interpretation, if you have a map such that all of these sets are definable and known to map, then we say that it's an interpretation. And the main thing that we are interested in is that if you have an interpretation, then you can rewrite formulas from A to formulas to M that are equivalent. But of course, because of these problems, we should be careful which formulas we use. And the most obvious solution is to use systems of equations to define your structures. And then you can as well define an interpretation, or interpretation by equations. So, and then following the usual algorithm of rewriting formulas, you can easily see that if you start with system of equations and you have an interpretation, then the formula that you will end up with is also a system of equations. But you can do a bit more. You can use what we call PE formulas, positive existential formulas, so the ones that don't have negations, and universal quantifiers. And this will also work the same. So in the end you will get a disjunctions of systems of equations, but if you can solve one equation, you can just check every of these systems of equations and see if any of them has a solution or not. And some properties, of course, rewriting property, the most crucial for us that I mentioned. And in particular, if you have an interpretation of A in M, and you know that the Diophantine problem over A is undecidable, then the Diophantine problem over M is also undecidable. And transitivity, of course, as usual, if you have one interpretation of C of A in B and B in C, then A is interpretable and C in an obvious way. So, what are some examples? Let's start with rings. I started with groups before, but I will talk about rings more. So, some of the trivial results, if you have a ring and you take all KR, then it is of course definable by the equation x is equal to ky for some y. But there are some non-trivial things, or trivial but not that trivial. For example, center of ring. If you look at it directly, that's a universal definition. But really, if your ring is finitely generated, then you can replace over all y only by finite generating set. And because it's a finite generating set, it would be a finite system of equations. And this will give us a definition. As example, bounded nil radical, so all x such that to some fixed power they give you 0. And moreover, if you know some basic structure theory of finitely z-dimensional rings, or in more general setting Noetherian rings, then the whole nil radical is of bounded degree, so it is E-definable. And yes, the E-definition is written there. Now, some more examples. If you have an E-definable ideal, then the factor ring would be interpretable, because what is your interpretation is just the standard map onto a factor set. And with obvious ring operations, you can check that it is an E-interpretation. For example, if you want to check that xy is equal to z, well, what's the equation in the original group? It's just xy is equal to z plus r for some r in your ideal. And then you can write equations that expresses that r is in your ideal if this ideal was E-definable or P-definable. So in particular, R mode nil radical is E-interpretable for finitely z-dimensional finite or Noetherian ring. And I didn't say it, but finitely z-dimensional just means that the abelian group is finitely generated. So for example, rings of algebraic integers are like this, and more. And some other example, if you have a direct sum, and say ring has an identity for simplicity, then both of these are definable. That follows from the fact that you can write your identity as sum of elements of these two R1 and R2, and it's very easy to check that this E1 and E2 will be identities in R1 and R2, and then this R1 would be just definable by equation E1 times some x, because these are ideals, right? So this is all very simple, but suddenly we can do a lot with this. So if you know some structure theory for rings, if you start with a commutative ring with, say, finite z-dimension, we just showed that the nil radical is definable, and we can factor it out. It's interpretable, and then it's a semi-simple ring. I'm not going into details, but it's a semi-simple ring. And then every semi-simple ring is a semi-direct sum of simple rings. Also very common fact. And it's a bit of a problem, but you can define also semi-factors as well. So what you can get from all of this, that for every commutative associative ring with identity, finite z-dimension, you can define a simple ring commutative associative with identity with finite z-dimension. And these rings are really just finite index subrings of O. And you can get rid of this finite index using PE formula, using disjunction. So really what we get is this theorem, very simple idea, but the theorem is kind of nice, that the Diophantine problem in particular over all commutative associative rings with identity, infinite of course, is the same as the Diophantine problem over all rings of algebraic integers, right? We can do the same with Q or with any reasonably good field or ring of scalars. So if you start with Q algebra, then you have a finite field extension and some other interesting, or not interesting, but some other cases. But really what's interesting is, can we get rid of these two conditions, that it's commutative associative and has an identity? Of course we can get rid of infinite, because there also everything is decidable, trivial. But what can we do to get rid of this? And for this it's really much more convenient to work with bilinear maps. So if you have a bilinear map and you view it as a two-sorted structure, you can also write systems of equations over this, and you can also define P interpretations and P definitions and so on. So if you have a bilinear map between just abelian groups, then we say that R is a ring of scalars if it emits a non-degenerate action on M and R such that it commutes with F. So F is R bilinear map. And of course, at least we have Z as a ring of scalars, right? Because Z already acts on M and N, and it's F is Z bilinear. And if both M and N are infinite, then Z actually acts non-degenerately. But also, there is a maximal ring of scalars, as I will explain in a second. And let's start with the case when F is non-degenerate, so F of anything non-zero and M and F of M anything non-zero is not zero, and linearly surjective, so linear span of the image is the whole N. So what we can do in this case? Well, first of all, any ring of scalars is inside of endomorphisms of M as a abelian group, because we want to have non-degenerate actions of R on M. So let's start with this one. Then we have this sim of F. So all alphas that commute with F. So if we move alpha to the left or to the right, it's the same. And you can see that again, any ring of scalars should be inside R2, because if you have a if F is alpha bilinear, then you can do this, right? So we can define this. Then you can define the center of this R2, so all alpha in R2 that commute with everything else. Again, this should be inside, any ring of scalars should be inside R3, because we want, I didn't mention it, but R should be commutative associative ring. So any ring of scalars is inside R3. And now, if you look at this first three define you an action of R3 on M, but we also want to act on N. And how we want to act on N is just by passing action from M. So what we want to say is that if you have F of M some element in N, then we want alpha to act here just by moving inside, because we already defined action of alpha on M. That's what we want, but that's not always well defined. So to ensure that it is well defined, we'll look at this. So if sum of F of something is 0, then sum of F alpha x y i's is 0. Right? And you can very easily see that all of these R1, R3, R4 are abelian subgroups of endomorphisms. And moreover, you can see that R3 and R4 are actually subrings and commutative subrings. And from what I said, R4 it really acts on M non-degenerately because it's inside of endomorphisms. And it also acts on N, and it also acts non-degenerately because our map is non-degenerate. And it acts on the whole N because it's linearly surjective, right? So really what it shows is that R4 is the maximal ring of scalars, because it is a ring of scalars by the definition, and you can really easily check that any ring of scalars is inside of this R4. And now what's interesting for us is that all of these are really definitions by first order formulas at the very least, because endomorphism of M, if M is finitely dimensional, so just finitely generated abelian groups, endomorphism of M is kind of matrices, right? So it's finite sum of M, more or less. So endomorphism of M is just indefinable. This is definition by universal formula, this is definition by universal formula, and this is also definition by universal formula because you can bound the number of sums very easily. You should be careful with defining multiplication because when you define the morphism of M in M, you don't have multiplication yet. But it can be done, not that hard. So what we can do is that if you have, for the starters, non-degenerate bilinear map, we can see that this maximal ring of scalars is definable. And if you have a finitely dimensional map, you can easily see that you can omit, you can only use E definitions because all of the stuff is finitely dimensional, so the same as for the center. What time do I finish?
In 20 minutes.
So it's the same as for the center. You can only write this equation, these equalities for generators. So that's more or less the idea. And this will show that for any bilinear map, at least like this, maximal ring of scalars is indefinable. And it's commutative associative ring with identity. And with some more work, you can do it for any bilinear map. So basically you make sure that it's linearly surjective by killing the part of M that it doesn't cover, and then you kill the annihilators of M and K. So really not that hard. So what it shows that for any bilinear map, there exists a commutative associative ring, max of F up to killing these annihilators and linearly surjective part, and equating M and K. That is interpretable in this three-sorted structure. In particular, if you have any finitely z-dimensional ring, not necessarily commutative, associative, or anything, nor with identity, then there exists a commutative associative ring with identity that is interpretable enough, because you just look at the bilinear map that is defined by multiplication and do all the same stuff. And moreover, it's really just, if you look at this, it's definitely not interesting. For example, ring that consists only from 0 is indefinable anywhere, so, or interpretable anywhere. So really what is important that it's actually some meaningful ring that you interpret here. And you can actually, for a given bilinear map, you can compute all of this stuff and actually compute your ring if you're interested in a particular bilinear map or in a particular ring. In particular, if you have a ring with non-trivial multiplication, so when image of multiplication is infinite, or R squared is infinite. I mentioned before that in this case, Z is the ring of scalars, is a ring of scalars. So the maximal ring of scalars will have Z inside. So the ring that we interpret there will also have Z inside. And this will allow us to reduce everything to this case of rings of algebraic integers. So really what this shows that if you have any finitely z-dimensional ring with non-trivial multiplication, of course, then the Diophantine problem is the same for this class as it is for the class of rings of algebraic integers. So that's very interesting, in my opinion, that there is no extra difficulty from gaining associativity or losing associativity or commutativity or identity. But there is really a difficulty here. You can't just easily go from any ring of algebraic integers to Z somehow. So, yeah. What can we say about infinitely dimensional rings? Of course, the stuff before directly won't work, because if you look at this, even endomorphisms of M are not definable, because in infinitely generated abelian group, you have endomorphisms that act on every generator, so you can define it in a finite way. But sometimes it's enough to have finitely generated, because if your M is a ring, then you can just define endomorphisms on generating set and then go from there. So, in particular, we can do a few results. A few of them are really easy. For example, if you have a ring of polynomials, what we can do in this case? If you have R is polynomials with integer coefficients, we can just factor out all polynomials of degree at least 3. And this is obviously an E interpretable in R with obvious factor map, because R cubed is just definable by an equation x is equal to y cubed, more or less after finite sum. So, and this is a finitely z-dimensional ring with non-trivial multiplication, and you can easily see that the maximal ring that you get from here is Z. So, just very easily, we see that for rings of polynomials, Z is E. I didn't say E, but it is E interpretable in this. So, in particular, the Diophantine problem over here is undecidable, which of course known, but it's a very simple way to see. Moreover, you can do it the same with free associative algebra. So if you here think about monomial of xi's that do not commute, you can still do the same, because R cubed is still indefinable. So, and this again will be a finitely z-dimensional ring. And again, you can very easily see that the coefficients there are actually Z. So, again, a very simple argument shows that equations over ring of over free associative algebra is undecidable, are undecidable. And this is also a non-result, but the previous argument was pretty long and complicated. So, I think that's, again, a very nice thing to know. And another result, free real algebra, you can do kind of the same. You should be careful what you mean by R cubed and make sure that it is E-definable. But really, because of the properties of Lie bracket, you can do kind of the same thing. Right. So now some stuff about groups. And the idea or the goal is the same for us, at least, to reduce problem to the Diophantine problem over rings of algebraic integers. And we can fully do it for finitely generated nilpotent groups. So the result is that if G is finitely generated nilpotent group, that is not virtually abelian, because if it is, then everything is decidable. Then there is a ring of algebraic integers such that it is E or PE interpretable in G. So that's very nice result, especially in the view of this paper that I mentioned before, that dealt just with free nilpotent group. And this can be easily obtained from our results. You can see that the maximal ring of scalars, or analog for it that we get, is Z in the case of free nilpotent groups. So it's undecidable. And moreover, for finitely generated nilpotent group, there is kind of a two-way reduction, because if you look at this group UT3O, so the same in triangular matrices, but with coefficients in O. You can easily see that for this group, the Diophantine problem is actually equivalent to the Diophantine problem over O. So again, we kind of have two-way reduction. The Diophantine problem over the class of finitely generated groups is the same as the Diophantine problem over all of these problems. We can also do it for certain metabelian groups, but not for all of them. And I don't think I will go into much discussion about it. But for certain metabelian groups, we can reduce it to important groups. But it's still not a problem what you can do or you cannot do in general case. And for more than so for solvable groups of big rank, it's known that the Diophantine problem is unsolvable. It's reducible to the arithmetic of integers, with multiplication and addition. And again, we can do it for certain polycyclic group. I'm not again going into details which exactly polycyclic groups, but in many cases you can find an important group inside. And I will state some open problems and finish on this for questions. So, as I mentioned, this result works for commutative associative family algebras because R cubed is indefinable and because this factoring is of finite dimension. But if you look at non-commutative, non-associative algebra, for example, just completely free algebra, not completely, but as with addition as an abelian group and multiplication. So multiplication, addition, and such that addition is a commutative operation, and there is a distributive property. Right? So you have an absolutely free algebra on multiplication, and then you have a free abelian group generated by all these monomials. So if you look at this algebra, this trick obviously doesn't work because you can look at something big like this, and if length of these two words is really big, then there is no way you can define this in a reasonable way. So it's an interesting question, in my opinion, what you can do with other free algebras. In particular, is it possible in any case integral Z or not? For example, the result that someone mentioned yesterday saying that in absolutely free algebra, if equations are decidable, so maybe actually in these equations are also decidable. I didn't think much about it, but maybe. Another open question, what about free associatively algebras with coefficients in some ring of algebraic integers? So it's known that for polynomial, you don't need actually this reduction, even if you put a ring of algebraic integers here. There's still, the equations are still undecidable here, even though our reduction gives us O in the end, so we don't get the answer. So, is there anything like this in general case, or there's a two-way reduction in this case? And for finitely generated groups, in particular metabelian groups, very interesting topic, I think. A very simple group, for example, bound-slug solitaire 1, 2 is one related group. So you can look at it as a matrix group like this. You have 1 over 2 to the n here, and here you have something that lies in Z extended by 1/2. So this kind of a very simple group, and it's very well known, and there is a nice presentation of it with just one relator, but we don't know if the equations are decidable or not, and we don't even we're not certain if they should be decided or not. So it's a very interesting problem. So that's it. Thank you.
Have you any question or remarks? Yes, Len.
So you mentioned at the beginning some result that for some structure there is a difference between the diaphragm problem for systems of equation versus a single equation.
Yeah.
So your reductions, they don't preserve this property, right? So they work for systems, but so do you know what kind of reducibility would correspond to this?
Yeah, that's a very interesting question, and I think recently there's been a lot of work in group theory in particular about single equation or bounded number of equations, and I think there is no established technique to work with this. Every time it's just writing equation implicitly and trying to see what it is like. For interpretations.
Yes.
Only a short remark. Maybe it would be better to replace the word maximal by largest.
Yeah, I know.
Maximal.
Yes.
That's it.
I know about it, but I don't think it's possible. It's kind of well-established term for some reason. But
okay, thanks again.